Hello, uh, good evening, everybody. You are welcome to the Elites Academy class, and as usual, we are going to be beginning from where we stopped in the last class. Now, for those who haven't watched the previous video we did, if you haven't watched the previous video we did the last time, which was last week Saturday, right, I implore you to go ahead and watch the video. You're welcome again. Now let's get into what we have today. Now just give me a second. Now, physics the second, right? Introduction to classical physics. Introduction to classical physics. Now, a quick recap, right? In the last class, we introduced the concept of classical physics, where we define classical physics as the branch of physics that describes the behavior of microscopic objects and physical systems using theories developed primarily before the emergence of quantum mechanics, which is the physics of small things, and modern physics, the physics of relativity and the speed of light. Now, in the last class, I did not really explain quantum mechanics and modern physics because those are different branches of physics, but just a little bit of explanation. Now, when you hear quantum mechanics, we are talking about the physics of small things, or the branch of physics that deals with smaller particles like electron, subatomic particles in general, right? That's what we like. Anytime we study quantum mechanics, those are what we study. That is what we base our study on. It is a branch of physics that deals with smaller and smaller things. And then we have modern physics. Now, modern physics helped in our understanding of massless particles, or particles that travel at the speed of light, right? That's what modern physics helped explain, at least a chunk of it, right? And then it also did justice to relativity in general. Right now, we referred to classical physics in our last class as old physics, right? Not because it is obsolete, but because it is based on the 19th century scientific revolution that kick-started what we know now as modern physics. That was one of the reasons. That was one of the reasons why we refer to classical physics as old physics, right? Because it dealt with a lot of things that happened between the 19th century and the 20th century. Because the 19th century and the 20th century was the peak point for our understanding of science as a whole, right? It was the peak point. Now, moving on, right? We focused on Galileo. The last class, we focused on a guy called Galileo Galilei, right? Galileo Galilei, right? That is his full name. The reason we focused on him was because he, as well as Newton and Kepler, were the three people that did a lot of work in shaping our understanding of classical physics, right? He enhanced our understanding in physics. Galileo specifically, and Newton did so much work on certain concepts. The first concept that Galileo helped clarify was the law of falling bodies, right? Now, remember, before Galileo, we had Aristotle. Aristotle was one of the philosophical minds of the time, right? That postulated certain views, right? He had certain understanding of the world, and even though those understandings were not based on experiments, they were based on his observation of everyday life. It also created, some sort of notion for the science at the time, and we talked about how at that time science, philosophy, and religion were considered natural philosophy, right? They were considered natural philosophy because there was a combination of the three. Even though science, religion, and philosophy do not go hand in hand most of the time, at the time of Aristotle, it was combined. And so there were lots of confusion because there were less experiments that were done on observations that were made. And one of the things that we talked about was how Aristotle postulated that heavier objects fell faster than light objects. Now, he was not wrong if you look at it from an observation point of view. He was not wrong. But the problem was the reason he believed so strongly at the time that heavier objects fall faster than lighter objects was because he looked at just the weight of the object, right? So he believed, or one of the things he accepted, one of the ideals that he accepted at the time was that the weight of an object is what determines how fast the object falls. So how fast an object falls depends on just the weight. He was very wrong, and we knew when Galilei came around and he did the experiment, the famous experiment where he was in a tall building that was called the Tower of Pisa. Right, where the Tower of Pisa is a tilted building that created an inclined plane where Galileo was able to drop, cannonballs of different weights, right? And he saw that in an inclined plane, right, objects of different mass accelerate at the same time, right? And he from that observation, he drew the conclusion that at the absence of air resistance, a heavier object and a lighter object will fall at the same time. Right? Galileo was what gave us that. He was the person that explained, that whole concept. He clarified that whole concept through the experiments that he did in the Tower of Pisa. Right? And because we are scientists, we have to do other experiments. The most famous modern day proof that we conducted to prove that Galileo was right was the Apollo 15 space mission that happened in 1971, where an astronaut named David Scott dropped a hammer and a feather on the moon. And the moon has no atmosphere, and because the moon has no atmosphere, there's an absence of air resistance, which means the hammer and feather, just like Galileo had postulated, fell down at the same time, right? So we knew, as we studied the last time, that at the absence of air resistance, right, a heavier object and a lighter object will fall at the same time. Now, moving on, right? Today, we are going to focus on the second thing that Galileo, alongside Newton, helped clarify for us, right? It's something that we call, or is a concept that we know today as inertia. Now, what is inertia, right? Quickly, during the Newtonian mechanics era, right, which was an era where classical physics was big, where physics in general was beginning to take experimental shape, right? The famous scientist at the time was Isaac Newton, and Isaac Newton gave us 3 laws in physics. But because of what we're studying today, which is inertia, we are going to be focusing on just the first law that was postulated by Newton. But I also, gave the 3 laws. I wrote down the 3 laws for you, but we're going to be focusing on just the first law. Now, the first law of Newton, or Newton's first law, states that an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an external force. Now, the reason Newton's first law is important to our study today is because Newton's first law is also called the law of inertia. Right? It's also called the law of inertia. Now, recall what the law states for clarity, right? right? A body will continue in their state of rest or uniform motion unless acted upon by an external force, right? Unless acted upon by an external force. Now, I want you to picture a car. I want you to picture two cars specifically, right? The first car is parked in a garage, right? And the second car is on the road, right? I want you to picture a car parked in a garage and another car that is on the way. Now, the car parked in the garage is in a stationary position, or what we refer to as physics as a body at rest, right? If you park a car in the garage, you turn the car off, that car or that body is at rest, meaning the car is not moving. It's a stationary car. Now, according to Newton's first law, a car, I'm trying to bring it down to the example now, a car being the body will remain at rest until a force acts on it, right? In the same vein, a moving car will keep moving until a force also acts on it, right? In the case of the stationary car, a force acting on it means starting the car or pushing the car or doing anything that will result to the motion of the car, right? So whatever the case, right? Whatever the case may be in terms of a force acting on a stationary car, whether it be you using the car key to start the car and move or pushing the car, unless a force is willing to act on the car, right? The car will remain in that position. It is the same case with a moving car. Newton postulated in his first law that a moving car will continue moving, right? It will continue moving unless a force stops the car. So whether the car is stationary or whether the car is moving, until the force acts on that car will continue in whatever state it is in. So the parked car will always be parked until somebody pushes the car or turns the car on using the car key, right? And a car in motion will continue in motion until somebody stops it, put a halt on it, like hold the brakes on the car, right? So Newton postulated that a body of mass has a tendency to remain in whatever state it is in unless it is acted upon by a force. Now, that tendency of a body to remain at rest or continue moving, or that resistance to change, is what we call inertia, right? So that resistance to either move from a stationary position or continue moving after it has been made to move, as described by Newton's first law, is what we refer to as inertia. Inertia is the tendency of matter to keep doing what it's already doing, right? Staying still or staying in motion, right? So since Newton's first law describes that property of matter, or that tendency of matter to remain in whatever state it is in unless something acts on it, it got named after inertia, right? In other words, Newton's first law was describing the inertia of an object, right? It is describing the tendency of an object to remain at rest or continue moving. That is exactly what Newton's first law was trying to address. That is the reason it became a law, because inertia is an important property of matter, right? A very important property of matter, right? And in this class, an explanation of inertia is is very necessary in our understanding of Newton's laws, right? Because Newton's third law is one of his famous scientific explanation or scientific postulations that we still use today in modern physics. But it was proven during the 19th century, or during the period where classical physics was beginning to take root, right, in our understanding of physics today. Now, a quick way to understand what inertia means, right? The law, Newton's first law, isn't really about forces causing motion, right? So when he said that a body will remain at rest or maintain a uniform motion unless acted upon by an external force, the emphasis in that law is not the external force that is acting on the body. The emphasis in that law is the tendency of the body to remain at rest or to keep moving. Right? So the law isn't really about forces causing motion, right? It's about what happens with no force, right? In other words, what does the body, ipso facto, the car in the example we used earlier, what does the body do when no force acts on it? Right? And we've just learned that the body remains in whatever state it is in, or the body maintains whatever state it is in until a force acts on it. But what we are trying to learn, the importance of Newton's first law, is the state of the body when no force acts on it. So even though a force there's a probability that a force will act on an object, thereby moving the object from whatever position it is in, or maintaining the position of an object. What Newton was trying to communicate in his first law was the tendency of that body to resist change. Right? To resist change. So let me give you an example. Right? Picture yourself in a car. In a car, let's say you are going from a location to another location that is farther from the location you were in, right? So you are in a moving car, and the car is really, really speeding, right? The driver of the car is speeding the car. Have you noticed that anytime a car is being sped up, anytime you are moving very fast in a car, or anytime the driver is driving very fast and immediately holds brake, do you notice that you usually tilt forward when the driver immediately holds the brake, right? You push yourself forward. There's this forward push, right, that happens when the driver immediately holds brake, right, after moving with that much speed, right? There's a tendency that when the driver holds brake, or when a force acts on the moving car to stop the moving car from moving, you tend to react, or whoever is in the car reacts by a forward motion. The reason that happens is because your body resists. Your body is much more aware of the motion, right? So your body is resisting change in that situation, and by resisting change, I mean it wants to keep accelerating. So even though you, as a reference frame in the car, is stationary, but the car you are in is moving. So even though you yourself is not moving in the car, but the car is moving relative to you, and because the car is moving relative to you, you have a tendency as a stationary body in the car to remain in that spot. So when the driver immediately holds brake, the reason you clinch forward, the reason you move forward, the reason there's a forward movement, right, is because your body wants to keep maintaining that forward flow that the vehicle you're in is in, right? Your body wants to keep moving, right? So another very important example that I give here in this study material is if I keep a book on a desk, right, as long as no one touches or pushes the book from that position I kept it, the book has a tendency to remain unmoved in that spot. Right now, the book's position does not change unless someone or something changes its position. That is what Newton's first law was communicating, right? And the tendency of that book to remain in that spot until someone moves it. That is what is known as inertia. Now, you have to understand that as physicists, when we think of these concepts like the first law of Newton, it is very, very imperative that you know that Newton's first law is not communicating primarily the tendency of a force to act on an object, right? Primarily, what Newton was trying to communicate to his audience through this law is the tendency of a body to resist change, and that tendency to resist change is what we know today as inertia. Now, this is an important distinction as we wrap up this class, right? It's a very quick class because inertia is a very important physics concept that we have to look at, and because there's no real depth in it, since physics principles build on each other, inertia is very, very important in this situation for you to understand, and you don't really need to go into much depth to understand it. Right. So finally, and more importantly, an important distinction: inertia is not the force pushing or pulling the book in the example I gave. Inertia is simply the tendency of the book to resist moving unless a force acts on it. In other words, inertia is not a force. This is very important, right? This last word is very important. Yeah, inertia is not a force. It is a property of matter. Right? Inertia is not a force. It is very important that you understand that inertia doesn't, based on what we've explained so far, inertia is not the force that acts on the object, right? It is the tendency of the object to maintain or to resist a change in whatever state it is in. Right? Now, I believe that you get it. Now, in our next class, hopefully, we will build on some of the results of classical physics. And until then, have a nice day.